And let's see. Oh, I have to plug in my pencil. There we go. So one thing from last time, or two things from last time, I left you a couple of problems. One problem was to show that you cannot make a piecewise linear knot with less than 6 sticks. And I will leave this to next time. You can continue to think about that. All right. Then the second thing from last time was to prove that there exists a checkerboard coloring of any diagram. That is to say, you draw a diagram, and it could be a multi-component diagram. Oops, not a very good choice in there. Our diagrams are all supposed to be, for our purposes at this time, have only 4 regular nodes, so like that, yes. So, I wish to prove that this can be checkerboard colored. And the question is, how would you do that? What will justify the fact that indeed you can do it? I can call this region black, this one black, this one black, this one black, this one black, just following along, making sure that, that if I go through a crossing, I stay in the same color, and then the others are white, the remaining ones, and all of that works out very nicely. But why? How do I know that this will always work? Perhaps you figured it out. I'll reveal the secret, or at least one way of doing it. There's really more than one way. One way would be the following, that you wish to assign a parity to each region. You want to call it either odd or even, white or black. And you could decide that the parity of the outer region is white, and that if you were to draw a line and cross the boundary, then you switch parity. So this will go to black. So then, that one was still white. And then if you wanted to know what the color of a region is in some complex diagram, you take the outer point and you take some point inside, and is this white or black? That's the question. Well, find a pathway avoiding the crossings from the outside point to the point involved, and check the parity. 1, 2, 3 crossings. 3 crossings from white will be black. All right, odd crossing, black. So B corresponds to odd, W corresponds to even. But now you have the question, how do you know that you will always get the same parity count independent of what path you choose? So you can then start to think about, well, what happens if I use some other path that will get me to this point? Perhaps I choose a different path altogether. Maybe I choose this path. And I count, and I get 1, 2, 3, 4, 5. Here I had 1, 2, 3, but the parity is the same. So now you're left with the question, how do you know that the different paths will always give you the same parity? So I leave you with that question, and I'm going to give you a different proof, okay? So the puzzle here is, puzzle to solve is why do all paths yield the same parity? So I exchanged one problem for another. But now let me confront you with a fact that you may know already, and then we'll talk about how you prove that fact, the Jordan curve theorem. Jordan curve theorem says that a simple closed curve in the plane divides it into two regions, each homeomorphic to a disk. And for our purposes, we're talking about really a very simple closed curve. It doesn't have to be just a topological simple closed curve. It can be a differentiable one, or it could be just piecewise linear, quite simple. But nevertheless, the complexity, the apparent complexity of the curve can be quite large, like this. And there is an inside and an outside, the inner disk and the outer disk. So if you would believe the Jordan curve theorem for the time being, why then we can certainly color the inside of a Jordan curve black and the outside of it white, and we will have achieved two coloration for a Jordan curve. And that, in fact, is a special case of a knot diagram where there are no crossings. So I will convert a knot diagram, or a flat knot diagram, I'll convert a flat knot diagram into a Jordan curve in such a way that I can get the coloring for the knot diagram back. So let me show you what I'm going to do. You can't spell today. How am I going to do that? Well, here's the knot diagram. What I'm going to do is very simple. I'm going to take the knot diagram. I'm going to leave a copy of it over there, and I'll draw another copy of it here. And then I'm going to walk up to a crossing, and I'm going to erase it. And then I'm going to reconnect that crossing in such a way that it's no longer crossing. There are two ways I could do that. I could do it this way, and I could do it the other way. I wish to retain, I'm going to assume that this is a connected diagram. For the purpose of our argument. So we're going to assume we start with a connected diagram. When I make this smoothing, I do not want to disconnect it because I'm after a Jordan curve in the end. So in this case, it didn't matter. I could do it either way. I'll just demonstrate. Now I do another smoothing here. And again, it doesn't matter which way I do it. It's still connected. Let me do it this way. But here it matters. Here it matters, but I have two choices. If I connect it this way, it'll be disconnected. But if I connect it the other way, it'll be connected. And one way or the other, will be able to make it connected. I claim. You can think about that. But now you have a Jordan curve, you see? So here's a Jordan curve. Diagram, Jordan curve. Color the Jordan curve, because the Jordan curve theorem tells you that you can. And now you see every region of the knot diagram corresponds to a place in the Jordan curve. You just put these crossings back in, put them in, take the same coloring, and put the crossings back in, and you have a checkerboard colored knot diagram. So it works. It works on the basis of the Jordan curve theorem. So, of course, it's possible to continue this discussion. You can ask, how do I know the Jordan curve theorem? So let's think about that for a moment. How do we know that the Jordan curve theorem is true? So you're facing a Jordan curve. And it's a reasonable Jordan curve. It's a tame differentiable Jordan curve. It only has a, and what I mean by that is that I will assume that if I were to take a point out here in the outer region, and I were to draw a straight line from that point all the way down through the curve, then it will meet the curve in a finite number of points, sometimes transversely, and sometimes tangentially. And that's all. And furthermore, you can see what will happen if I take such a ray and I change its direction a little bit. Suppose, for example, that I change the direction of this ray a little bit. Now you see it's tangent here. Actually, it's not quite tangent. It got 2 points. And then on the other side of tangency, if I drew another one, the 2 points disappear as you go across the tangent. Or here, the same thing happened. You had 2 points, and you went across the tangent, and you lost them both. On the other hand, you gained these two. No, you didn't. They just went along over here. So you see what will happen if you move a line. When you move a line, you may go from here to here, and the parity of the number of intersections remains the same. The number of intersections changes, but the parity remains the same. If it's even, it's even. If it's odd, it's odd. And consequently, if I were to take a point in the curve, if I were to take a point somewhere in the plane and draw a point from a point given to be outside and over to that point, then the parity of the number of transverse intersections is going to tell me whether I'm outside or inside the curve. So I can designate any point as being outside if it has the same parity, and if it had the opposite parity, like this one, then I'm inside. But what I want to do is use, now you see why the parity argument would have worked for the knot diagram, but you'd have to make a more complicated argument for the knot diagram because the intersections would be more complicated. Here the intersections are very simple: tangency or transversality. So I can assign a parity to every point in the plane that's not on the curve. And I call all the ones that are odd the outside, and all the ones that are even the inside. But now I need to do a bit of work, because what I want to show is that if the parity of P is equal to the parity of Q, then there exists a path from P to Q not crossing the Jordan curve. Then we will have what we want. I'm not going to go all the way to proving that the inside is a disk and that the outside is a disk minus a point, but I will show you that if 2 points have the same parity, then they can be connected to one another. And how is that going to happen? Let's take this point, which has parity 3, okay? So it has parity 1, and it should therefore be able to be connected to this point here. So I want to show you constructively how I will get that path. What I'm going to do is I'm going to take one of the points. So I have a point P and a point Q. And we have that let's write pi of P for parity. Okay? So I have that the parity of P is equal to the parity of Q. They're both odd. I walk from P over to the curve. Now I walk along the curve. Not crossing it. Of course, I made a mistake, didn't I? Because I said the parity of P is equal to the parity of Q, but here the parity of P is not equal to the parity of Q. But let's take another point, Q prime. And the parity of P is equal to the parity of Q prime. I miscounted when I looked at it, right? Q prime over here has parity 2, even parity coming from outside in, and this has parity. So I do this. I do what I said. I go over to the curve and I walk along the curve, and I keep walking along the curve, and eventually, I will come to a place where I am near that point. That point is somewhere, and sometime I will be near that point. But furthermore, I claim I'm going to be near that point and in the same region, not in an opposite region like I was here for Q, you see? And then I will connect over to it. And that tells me how to get the path. But now I have to justify to you that I am going to be near the point on the correct side. But that's our parity count again. Because if you are looking at rays that, I'll leave it to you to think it through. It is just the parity count again. And as long as the curve is reasonably tame so that it doesn't have infinitely many wiggles in it, you can do it this way, and you will know that, in fact, the Jordan curve theorem works. So the Jordan curve theorem is what lies behind the checkerboard coloring of curves of knot diagrams in the plane. So you can think about the details. But I do want to show you how it is different if we had how it's harder if the curve was more complicated, or if some other things should prevail. So let's look at some examples, and then we'll go on to the knot theory again. If the curve has infinitely many wiggles. The problem is more difficult. And that's why you will see subtle proofs. You may wish to try some examples. For example, I could spiral in forever to a limit point and then spiral back out. Now, that's not so bad. It's only got one bad point down there. But that means that if I were to take, if I'm not careful, and I were to choose a point and a line, that line could intersect the curve in infinitely many points, right? Here, a straight line could intersect the curve in infinitely many points. So the parity argument would not work there. You see? So if you have curves with a lot of wiggles in them, and of course it could happen another way. You could have something that was doing this, even as simple as that. And then you could have a certain straight line that intersected it in an infinite number of points. So if you assume that it doesn't do that, that it is basically tame in that sense, then the Jordan curve theorem is a matter of counting parity. And that's all we would need. So for example, if our curves are basically piecewise linear curves, then there is no problem in using the Jordan curve theorem in a very elementary way. But if you allow certain kinds of infinite constructions, then you can have much more trouble, and it's more interesting to try to prove the theorem. Not only that, but there is another example which is worth your while seeing. Let me, excuse me, I just want to make sure I'm saving the slide. Now let me take this away for a moment. So here's a very famous example. We're now in 3 space, and instead of looking at a simple closed curve in the plane, we're looking at a 2-sphere embedded in 3 space, but embedded in an infinitely wiggly way. It has an infinite number of branchings that go on. You can see how this is a limit process, which is leading to an embedding if you're careful. You start with the lower sphere, just nice sphere, and it extends to arms. But then each arm branches into 2 arms, and those branch into 2 arms, and they successively link each other like a simple hop link, like the ones that we talked about of linking number 1. But it keeps on going forever and forever and forever, off to limit points. And then you have to think about the limit point structure of this, which is Cantor set. And you have to think about how it really is an embedding of a 2-dimensional sphere in 3-dimensional space. So this is like the Jordan curve, a very infinitely wiggling 2-dimensional Jordan sphere in three-dimensional space. This is called Alexander's horn sphere, due to J.W. Alexander. And what happened here is that after you go to the limit, the interior of this is a ball, topologically, but the exterior is not a ball at all, very far from being a ball. And if you want to read more about this, look up the Alexander horn sphere and you'll find out more about it. So this is showing that the analog of the Jordan curve theorem does not hold in higher dimensions. This is a beautiful example which explains how that happens. But of course, it does require infinite construction in order for it to not hold. So I couldn't resist showing you that. I'll put a copy of this picture of the Alexander horn sphere into the Dropbox in case you want to look at it. It can be found in the old but rather well-written book on topology called Topology by Hawking and Young from a long time ago. That's where the picture is found. Although you will find other pictures of the Alexander horn sphere if you go looking for them. But what about our checkerboard problem? Our checkerboard problem also changes if we were to look at it in other circumstances. We have that if you draw in the plane any curve or curves transversely intersecting like that, then you can checkerboard color. And that has a consequence, as I said last time. It has a consequence, and let's recall the good consequence of that. The good consequence of that is that if you were to then go up to every crossing, shaded as it is by the checkerboard coloring, and put in a crossing, an actual not weave crossing like this, in such a way that when you rotate the overcrossing line counterclockwise, it sweeps out the shaded part. You can do that at every crossing. Just choose to do that. Then you get an alternating outer link. So let's just see that happen here. Let me do a sketch and do it again. So there's my coloring. And then I go up to each crossing and I say, okay, I'm going to fix you, I'm going to fix you, I'm going to fix you, and you, and you, and you, and you, and you. And I don't have to look at anything nearby. I just look at each one and make sure it's that kind of a fix, like that, like that, like that, like that, like that, like that, and so, and so. And I get an alternating knot as a result. Alternating meaning that it goes over and then it goes under and then it goes over and under and so on, back and forth like that, alternating. So checkerboard coloring implies alternating. Now, what happens if you were to draw on some other surface rather than the plane? Let's take a look. Here's the torus. And here's a four-regular graph on the torus, a very simple one, consisting of these two curves, one going around in the longitudinal direction on the torus, and the other is going around the meridional direction on the torus, and meeting right there. So what will happen here if I were to try to make a checkerboard coloring. I would want this to be black, and I would want that to be black. But you see, if you remove this curve and this curve from the torus, if you take the torus minus these two curves, it's homeomorphic to one rectangle. Just one rectangle. And that means that I couldn't possibly color it with two colors so that I had two different colors across an edge, because you can get from one side to the other. And that's just the way it is. If I were to work a little harder and make my graph a little more complicated, then I could checkerboard color it sometimes. But in general, if I have diagrams on higher genus surfaces, then I will not be able to checkerboard color them. And we can come back to that question later about checkerboard coloring diagrams on higher genus surfaces. But as long as we're talking about higher genus surfaces, I think I want to tell you about a way of thinking about knots on such surfaces. So I ask you to consider knot diagrams drawn on a higher genus surface. For example, on a torus. Now, I really mean knot diagrams. I mean that you're going to be allowed to have some weaving going on, just like when you draw a diagram in the plane. Let's take a look. I'll change color to make a black knot diagram. I could have somebody like this. A little bit of weaving, as I do in a trefoil diagram, right? And then it might wrap around the torus like this, and wander over here, and this one could wander this way and come on back over here, and this one like that. And there is a diagram which is supported on the whole of the torus surface. And we can do Reidemeister moves for knots, for knot diagrams on the surface. So you see, if I choose a surface and draw knot diagrams on it, it has its own knot theory, a different kind of knot theory from the knot theory of drawing on a two-dimensional sphere, which is where we were drawing before, or on a plane. You can draw on the surface of a two-dimensional sphere, you can draw on the surface of the plane, you can draw here. In some cases, of course, some of the knots that I might draw on this surface, I'll draw another one over here, would really not belong there, like this knot here. This knot here really is belonging in the plane. There's no reason to have it in the big space of this torus. It isn't using the torus. But this other knot that I've drawn, call it K, and here's trefoil, the knot K over here, that really seems to be using the surface. If I push it around, it won't slide off the surface into a little local knot like that. So I have a knot. I can do knot theory on surfaces, and this is quite an interesting question. how to classify the knots, the knot diagrams that would belong on a surface. These can be regarded as S1 going into the surface, in this case the torus, crossed with the unit interval. You see, this is the three-dimensional space involved. You take a torus, you cross it with a unit interval. Now you have a thickened gadget like that. And the knot is embedded in there, and the weaving means that you went up and down along that interval as you were going along. So you can understand, we'll come back to how we would deal with this, but you can understand that we can think about knot theory in surfaces other than the two-dimensional sphere or the plane. And now I give you one that I bet you'll enjoy thinking about quite a bit, that I plan to come back to. Let me save this one. What about knot diagrams on a Mobius strip? Now you're all familiar with the Mobius strip. Mobius strip is a piece of paper which has been attached to itself so that it's a band like this, but it has a 1/2 twist in it like this. So it's like that, and it twists over so that here so it has only one side. Mobius strip M has one edge and one side. Because if you started on the top of this and you walk around, you'll find that you come back underneath. If you were standing up on the Mobius band here, right? And you decided to take a walk, well, the very first thing that happens if you're walking in this direction is that you find yourself down here, right? And then you keep on walking, and by the time you get back to where you started, you're not back to where you started, you're still down there, over there like that. So when you got back to where you started, you're on the other side of the Mobius band. And now I say, here's something for you to think about. Suppose that you consider a knot diagram that you've drawn on the Mobius strip. Maybe you drew it locally like that, right? And then you're looking at the knot diagram with your eye above the plane like this, yes? And then it goes through the strip and comes out on the other side. I mean, it goes through the twist and comes out on the other side, and now there's an eye that's below that looks at it. This eye that's looking at it is no longer looking at it. You're looking at it from the other side of the strip of paper. So the question is, how will you do a knot theory here? How will you do a diagrammatic knot theory? So I leave you to think about that. And now let's go back to where we were. All right. So let's recall where we were, unless you have some question about my questions. I've been raising various questions here. Any questions from you? Everybody can hear me, I hope. So let's now recall the definition of the unoriented quandle. And let's go back through some things we said about it. Now, the definition of an unoriented quandle is that it's a set A, and there is a binary operation star, and it satisfies three axioms. A star A is equal to A star B is equal to A, for any A and B, and A star B star C is equal to A star B, A star C, star B star C. And we have explained before that each of these corresponds to a Reidemeister move. Let's recall quickly. In the case of the first Reidemeister move, you're looking at the diagram A, and A star A. And so it makes very good sense that A star A should be equal to A, so you could add or remove curls. In this case, it corresponded to a second Reidemeister move, because you may have B coming along here, and then it's still B all the way over. And here you have A, and here you have A times B. And here you have A times B times B. And if this is equal to A, then you can pull that out, and you can correspond to the second Reidemeister move. And over here, you have AB, A times B, and this is C, and here you have A times B times C. But if you move the line down, like that, then A will meet C first, so you'll have A times C, but B met C, so you'll have B times C, and then coming out over here, you'll have A times C times B times C. And so, again, it makes sense that you should set these two equal to one another, and then things will be then the algebra will correspond to things that have to do with invariance under the Reidemeister moves. So let's go back and look at this again. Take the trephone knot, and label the arcs by some arbitrary elements of some algebra, and then write down for each of the crossings, crossing number 1, crossing number 2, and crossing number 3, the corresponding relations that have to ensue in the Quandl. Well, as we walk along at 2, we see A times C equals B. And then I keep on walking on it. At 1, I see B times A equals C. And I keep on walking on it. I get C times B equals A. Those are not the only relations that I can write down that follow from the Quandl. For example, I can walk backwards. And if I walked backwards, then instead of seeing B times, B times A equals C, I would see C times A equals B. I'm walking backwards. C times A equals B. And then I would see B times C equals A at B times C equals A at 2. And then at 3, I would see A times B equals C. See, I actually get 2 relations at every crossing, but they come to one another through the Quandl, because if you take, for example, B times A equals C and use the Quandl rules, then you have B times A equals C times A. But by the Quandl rules, this is B equals C times A, and that's the other one that I wrote. C times B, where are we? B times A equals C. C times A equals B. Yeah, that was C times A. Yeah, C times A equals B. Here, A times C equals B, B times C equals A, C times B equals A, B times A times B equals C. 2 relations at every crossing. And then we could try for a multiplication table and see what we can say about the Quandl, any Quandl that would fit the trefoil knot. So we have A and B and C, at least those. And we know from the axioms that A times A is A, B times B is B, and C times C is C. Then up here we have A times B. Is that given? Yeah, it's C. What about A times C? Oh, there it is. It's B. And what about B times A? Oh, that's given. C. And B times C? There it is. A. And C times A? B. And C times B is A. So in fact, this was our little 3-color Quandl structure, but you see it's a consequence of asking for a Quandl that labels the trefoil knot. It isn't just an invention of a metaphysician who wanted to create a universe that had 3 elements in it. It is, in fact, the very Quandl that is a consequence of trying to make a Quandl for the trefoil knot. And in general, what we're going to do is we're going to take a knot, K, and we're going to define the Quandl of that knot is going to be equal to one which is described by generators and relations. And the generators are the arcs of the diagram, and the relations are the equations that occur at each crossing. And then you have to take the Quandl that is the consequence of that. So let me go to another slide to tell you about it in general. So I have some knot. Maybe we'll draw one for the sake of having one around another knot. And I have a couple of arcs in the knot. Maybe I have A, and maybe I've labeled it with letters, C, D, okay. A, B, C, and D, 4 letters. And I choose a crossing, and at every crossing I get a relation, you see. So I get a relation here that says that B is equal to A times C. But in general, what am I going to get? I'm going to get that the Quandl of a given knot is going to be given by generators G1 through Gn and relations R1 through Rn. How many? Rm anyway. We can worry about the count later. But these correspond to the crossings. And these correspond to the arcs in the diagram. And at every crossing, we write down one relation. It's really 2, but we only need to write down 1 because if B is A star C, then A is B star C. And then what we mean by this is the universal algebraic construction of a quandl, meaning it has to satisfy the axioms, with these generators and relations. Now, it's possible you're not familiar with the universal algebraic construction of an algebraic structure, but it's a simple idea, and you may have seen it before for groups. If you've seen it before for groups, the analogy is exact for any other structure like the Quandl. What you do is, just fixing that, you can consider all words in the generators. Now remember, this is a non-associative thing, so you look at all words in the generators. Example, in terms of this knot, A times B times A times D times B, a typical word. It has to be associated because it's a non-associative algebra, you know that. Modulo the equivalence relation generated by 1, the relations, and 2, the Quandl axioms. So that simply means that if you had 2 words, and you could get from one word to the other word by some combination of using the axioms or using the relations, then those 2 words would be considered equivalent. And then you take the equivalence relation on all words generated by that, and you get the universal algebraic construction of the Quandl involved. Now, of course, it's not something that you can know directly very easily, except in special cases. But in fact, we just did find out everything we needed to know about the universal algebraic construction of the Quandl for the trefoil knot. Let's look back. Because we just did exactly what I told you we should do. We found out what the products were in this case of any 2 elements. And we found out that these are the products. And knowing these are the products, we can figure out whether 2 words are equivalent or not. So we know the equivalence relation just from that. Very easy. So for example, if I wish to find out what happens to A times B times C times A, then in this case, that's very easy. I get to reduce it to one of A, B, and C. A times B is C. C times C is C. C times A is B. And I found out that that's B. And if I had somebody else and it also equaled B, for example, B times B equals B, why then I happen to know that B times B is equal to this. And therefore, these 2 words are equivalent. So speaking of the set of words is a way of doing it so that we can talk about the most general case. We will not always be able to just simply calculate a least example, but in this case we do. Now, what is the advantage of saying it in this algebraic form? we can then say this. We can say that if K is equivalent by Reidemeister moves to K prime, then the Quandl of K, that algebraic structure, is isomorphic to the Quandl of K prime. So the Quandl structure itself, the algebra that we associate to the knot, becomes an invariant of the knot. So that means that our little table, instead of thinking of the number 3 as the invariant of the trefoil knot, the Quandl of the trefoil knot is equal to the Quandl defined by this little multiplication table, right? I'll just write it again to remind us what's going on. So this is the algebraic structure. And if you were to take any other knot that was equivalent to a trefoil knot, you would calculate and find out that its Quandl was the same. You would find out that you would get that Quandl. So you have an algebraic structure, which is an invariant of the knot. And so we can think about it that way, and we will. So I wanted to say that generality to you, but now I want to do another example. What about the Quandl of the figure 8 knot? Can we figure that out? Let's give this a try. I'm staying in this abstract algebra mode, okay? We're just going to write down the relations and see what we can say about the Quandl of this knot. Okay, so let's give it a try. We're going to write down the relations for each of the crossings, and there are 4 of them. And then we're going to try to construct a multiplication table for this Quandl and find out how it's actually structured. So let's see. At 1, we have A times C is B. And we also have B times C is A. At 2, we have D times A is C. And we also have C times A is D. At 3, please yell at me if I make a mistake, huh? D times B is A. And A times B is D. And over here we have B times D is C. And we have C times D is B. So now I want to make a multiplication table and see if I can make it work. Of A, B, C, D, A, B, C, D. So let's put in all the information we know. We know that the square of everybody is equal to itself. Now we have A times C is B. A times C is B. B times C is A. B times C is A. D times A is C. C times A is D. D times B is A. A times B is D. B times D is C. C times D is B. I didn't fill out the whole table. All right. But I'm also not happy with having brought it all the way down to the bottom of the slide, so I'm going to move this up a little, and then I can move this up a little. All right. So you're looking at it, and you want to fill it in, right? There's more. I want to fill in more if we possibly can. So let's see what would inevitably have to be filled in. What about A times D? We're going to assume that it works the way it appears to work, namely that you're not going to have any repetitions in a row or any repetitions in a column, all right? No repetitions in a row, no repetitions in a column. So each row or column should be a permutation of the elements above. Now, what could A times D be? It cannot be A, it cannot be D, it cannot be B, and it can't be C either because there are going to be no repetitions in a column or a row. A, B, C, D. That means it's not any of them. It's going to have to be an E. Oop. We need one more. We need at least one more. Could be many more, but we'll try. I'm going to need an E. So I'll add an E. E is the product of A and D. Let's see, A over here and D over here. So it isn't occurring on the knot diagram itself. That, of course, was quite possible that that would happen. So there's E. Now let's keep on going using the principle of Sudoku, right? That I want to get different, I want to get permutations of all the letters along a row. So here we have A, B, D, and E. We have to have C here. This will have to be C. Okay. What else can I force? What about over here? B times A. It can't be A or B or C or D. A, B, C, D. So it has to be E. So there's E. But now we have E, B, A, C, and this will have to be D. And we have E, C, B, D, so this will have to be A. What else do we have here? What about this one? It can't be A, it can't be D, and it can't be C, and it can't be B. A, B, C, D. So again, it has to be E, forced to be E. But now A, D, E, C, so this has to be B. What about this one here? This one can't be B, C, or D, or A. A, B, C, D. Can't be A, B, C, or D. So it must be E also. And here we have B, C, D, E. So this has to be A. Now we're on the home stretch. A, B, C, D. So this has to be E. A, B, C, E. This has to be D. A, E, B, C. This has to be C. And A, D, E, C. This has to be B. And we filled it in. Now, that's not enough. Now you have to check that this multiplication table satisfies the Quandl axioms. Not obvious, but it does. You can try it. Try it. For example, choose at random 3 elements and see what happens to the distributive law. Let's just do it for fun. Getting myself a little bit of space. Let's try the distributive law out on some 3 elements. Say it's C and let's say A, B, and E, all right? So, so we can try A, B, I'll stop writing the star. A, B times E, okay? So let's see what we get there. So we get AB is D times E, and D times E is B. Now you can try AE multiplied by BE, and that's going to be equal to AE is C, and BE is D, and CD is B. It worked. And you will find that indeed, this is a Quandl. It wouldn't have been obvious before the hints that the figure 8 knot be provided for you to find a 5-element Quandl like this, but there it is. And that algebra structure is the invariant of the figure 8 knot. It has 5 elements. It doesn't have 3 elements. This is proving to us that the figure 8 knot is not equivalent to the truffle knot, and that both the truffle knot and the figure 8 knot are non-trivial knots. Now, I think I actually showed you a simpler kind of calculation to get a Quandl the last time by coloring with numbers. And this one turns out to be isomorphic to the one obtained by coloring with numbers. But I do suggest for algebraic understanding that you can try some other knots in the knot table and see if you can produce the multiplication tables for their Quandls. For the first few small knots, you will have finite multiplication tables, and then there will be ones that are infinite. And I will check for you when that bifurcation happens at first time. But we can see an infinite Quandl actually very easily. Let's do that.
Sir?
Yes, question?
Yeah, sort of. So, we did this Sudoku forcing of the table. Is that what induces the table to have the Quandl axioms? Like, why is this table obeying the Quandl axioms? You didn't explicitly put that in, right? You just did the Sudoku forcing.
I'm sorry, I don't quite understand what you're asking me. Maybe a good strategy here would be for you to write that question into the chat line right now.
I did.
Oh, that's what you wrote. You wrote, did the Sudoku forcing of the table make sure the table obeys the Quandl axioms? No, it didn't. You're going to have to check them.
No. We assuming we check them. I think it is true, right? First of all, like this table. I'm saying, where does that result from?
I think you could make a more abstract argument than I did. It is the case. Let's consider this. Thank you. That's a good question, and let's see what we can say about it. Let me go back to my screen. I hope I saved this in number 13. Let's just double check.
I guess one way to put it would
Yeah, I
be that.
did. Okay, okay. Now, I just want to get myself some room to draw. All right. Now, consider a row in the Quandl table. So you have, for example, A, B, C, D, E, and so on. And then you have R, S, T, U, V, and so on, all the products with, say, A, all right? So this is A times A, this is A times B, and so on out. And and so what I'm doing is I'm taking A and I am multiplying it by B, A, B, C, and so on, right? And I claim that that will yield a permutation of A, B, C, and so on. If this is a list of all Quandl elements. All right. So I need to prove that. That was my Sudoku principle. So I need to prove it. I need to prove that I actually will get a permutation when I multiply on the left. And similarly also when I multiply on the right. Let's multiply on the left by X and on the right by Y, let's say, okay? And now one of them is easier than the other, I think. I can define, for any given Y, I can define F sub Y, taking the algebra to the algebra, by F sub Y of A is equal to A times Y, right? And it has an inverse, right? Because I can multiply by Y again and I come right back to where I started. So F sub Y is equal to F sub Y inverse. And therefore 1-to-1 and onto. And that tells me that the columns are being permuted. So every column is a complete permutation. Now, I didn't think about the row. How do I know that the row is going to be a permutation? So I'm looking at A times Y. I'm looking at the problem is sorry, I'm going to leave that as something to think about because I don't immediately see what probably is an obvious argument that will tell me that the rows are permuted as well as the columns. But you're going to need that in order to be able to deduce that you really are getting the Quandl from the Sudoku principle. Does that answer your question partially?
Yeah, it does give me an idea.
Yeah. Okay. It's just that I don't instantly see how I'm proving that the rows are going to be permutations. So so let me just mark it as a question. Show that both rows and columns are permutations.
Can I ask a follow-up question?
Mm-hmm.
So if you can prove this, is it clear that having this multiplication produce a permutation forces the table to satisfy the Quandl axiom?
No, I don't think I still don't think it's clear, right?
Because if it were,
I don't think it's quite clear. Usually, as I say, people say, oh, well, we make it satisfy the axioms by dividing by the equivalence relation. But if you should get an example where it already satisfies the axioms, then the equivalence relation is very clear. But it isn't obvious logically to me, just on the basis of making the table, that it will automatically satisfy the axioms.
Because if the permutation principle did satisfy the axioms, you wouldn't need to double check. That would be useful.
That would be
But
indeed useful. And of course, you don't know how many extra elements you need to add either in general. So there are a lot of puzzles here, some of which may be easy to answer now that we've asked them. So we will just mark this page with a question, which we'll try to come back to.
I mean, apart from the Sudoku point, there is also the input from the knot itself, right? The knot gives us some relations as well. That, along with the Sudoku forcing, is what is giving us a Quandl. It can't be just one of them.
So where are we now? We have that some cases we can actually write the Quandl out, and we have some questions about whether certain things are forced automatically by trying to make the tables. Okay, and I promise to find out what I should know or what I really don't know by next week about those questions. Okay. So let me go on with an example that I had in mind. Let's save that. So here's a link. And what's the Quandl of this link? Well, you give it a generator for one and a generator for the other. And the Quandl of this link, the unlink of two components, the Quandl of this unlink of two components, is given by generators A and B and no relations. That's all, folks. You see, you can write, that means that you know that A, I'll stop writing the star. You know that A squared is A. You know that B squared is B. You know that you can write AB. You know that you can write BA. You know that you can write AB, A, B, A, and so on. And there are infinitely many things that you can write. Nobody said they commuted. And in fact, you ought to keep track of the order of your parentheses as well. And then what would happen if you took this link? Now you have A here, and you have a B here. And you have that A times B is equal to A. And you have that B times A is equal to B. And of course, A times B equals A if you multiply by B on both sides, becomes the same thing. So this doesn't have anything very interesting going on, right? But you have B times A is equal to B. So the Quandl of the hop link here is given by generators A and B, such that AB is equal to A and BA is equal to B. So another way of putting it would be it's given by generators A and B such that A times B is equal to B times, oops, I'm sorry, that's not right. Nope, I'm not getting anywhere further, okay? So that's a good pair of examples. And again, we're getting many elements. This one is generated by A and B with no relations, and this one has relations in it. And so you can analyze the linkedness of this by pointing out that the fact that it's linked is related to the fact that its Quandl is non-trivial. And nevertheless different from this one, but you're going to have to do more algebraic analysis even on this one to be clear about everything. So I will leave it, but you can look at those two examples and think about them. I feel like there's something further I wanted to say about this example. Let me look. No, I guess not. But as long as we're talking about general algebraic things, I do want to show you an interesting identity, a general identity. Suppose that you had x times y times z, associated in that funny way, like that, right? Can you get a better identity out of it? You know that if you have x times y times z when it's associated this way, then the distributive law lets you turn it into x times z times y times z, right? So I want you to take a look at the following. X times z times y, and then times z. And excuse me, I'm going to, I was using up space here in a bad way. So let's just create a little more space over here. I would like you to do a little exercise for me. Distribute this. And what do you get? Let's do it carefully. I can distribute the z in, and I get x times z times z. And that times y times z. Yeah? Right? That's right. But x times z is just x. So you see, this tells me that if I have something which is not left associated, then I can turn it into something that's left associated by rewriting it. In thinking about the algebra of it, this is useful fact, that every product that you ever write can be assumed to be left associated by means of this little trick. Enough about the abstract algebra, and we're almost out of time. Let me go back now to where we were with this. and I don't remember if we did very much of this, but I'm sure we did enough. So let me again do it a little more theoretically. I am interested in making linear quandles. And what I mean by linear quandle is that the operation A times B would be equal to RA plus SB, where R and S perhaps are elements of a ring, well, let's say of the integers, and A and B belong to some module. So, for example, ever Z or Z mod n. So, so basically, I'm saying that I think of the values in just use. You could say just use the integers or the integers mod n for some n. Now, I think this goes back to where we were before, but let's figure it out now. What would make a quandle if I used a rule like that? Well, let's find out. So if I take A times A, that would be RA plus SA. So that would be equal to R plus S times A. So we could assume that R plus S is equal to 1. Okay. Now what about the second rule? A times B times B. Well, that's going to be R times A plus S times B plus S times B. And that's equal to R squared A plus S times R plus 1 times B, right? Mm-hmm. RS plus S. Yes. So we want R squared equal to 1 and S times R plus 1 equal to 0. Get rid of that. Mm-hmm. Now, if R is equal to minus 1, then R plus S equals 1 implies that S is equal to 2. That's interesting. If S equals 0, which is another way of making that equal to 0, then R equals 1, and it's not interesting. Right? That would just be A times B is equal to A. Just not interesting. But this one's interesting, and this says that A times B is going to be equal to minus A plus 2B. And that will give us a rule which satisfies the first two Quandl rules. And in fact, it satisfies the third as well. And I think we talked about this the last time. Let me take a few more minutes so that I can go into this again from this point of view. Sorry, I ran into a little problem here. Little computer problem, sorry. There it is. So let's finish that. We're going to have A times B is equal to 2B minus A. And then you can check that A times B times C is equal to A times C times B times C. And I'll leave it to you to check. And this means that we can build some quandles just based on simple arithmetic. And I think we did this last time, but now I've gone through the background theory and that's helpful, but we want to go farther with this. But let's go back to the truffle knot now and give it a try. As I said before, if I take 0 and 1, then this would have to be 2. I'm just choosing beginnings. And 2 times 2 is 4 minus 1 is 3. And that tells me that I should be in Z mod 3Z. And then you get the 3-color quandle using the numbers 1, 2, and 3 in the modular number system using this. So the 3-color quandle comes back out. If you take the figure 8 knot and try the same work, again, just trying beginning numbers, then you find you're in Z mod 5Z. You get 0, 1, and you get 2. And then you get 2 times 2 is 4. And then you get 2 times 4 is 8 minus 2 is 6. And 6 must be equal to 1. And so we're in Z mod 5Z. And we've only used the colors 0, 1, 2, and 4. We did not use 3. In coloring the knot itself. So there's your A, B, C, D, and E. And if you work out the multiplication table, you can do the following. You can show that the multiplication table for this Z5 quandle is the one we found by Sudoku. So in terms of puzzleist nature, this is one way to make sure that the Sudoku table really does satisfy everything, because you know that this satisfies everything. And they're isomorphic tables. But finding these modular number system quandles is quite amusing. And what you basically have to find out is the modulus involved. And you can try this out on other knots in the tables. So a nice problem is to take a knot in the knot table. And find out as much as you can about its quandle. And the first approach is really quite easy. You try doing the Fox coloring. I call this Fox coloring in on a modular number system in this way. You can try out the Fox coloring and find the modulus by doing a bit of algebra, a little bit of matrix algebra, as we can explain next time. And then you can go ahead and see what you can say about the Quandl in general. So it's easy to start doing an investigation of this kind. Notice, I just want to tell you another problem or two, and then next time we'll talk about the oriented Quandl and the Alexander polynomial, and then we'll be going on to the Jones polynomial and other things after that. But there's something very interesting that you can notice here, and that is, as I said, that you only used 4 out of the 5 colors. But we can make some remarks. One is, you can prove that you can't use less than 4 colors. On any non-trivial Z5 coloring of a knot. It isn't restricted to there are many knots that can be colored in Z mod 5, not just the figure 8 knot. And if you have one that can be colored in Z mod 5 in a non-trivial way, then you will be unable to use less than 4 colors to do it. 4 is the minimum. And an easier, that's not hard. You should try proving it. An easier thing is to show that there are other diagrams. There exist other diagrams that demand all 5 colors. By which I mean other diagrams of the figure 8 knot. You start with some knot which isn't using all the colors that are available. It's not at all hard to show that you can make other diagrams that will demand all of them. I leave it to you to think about that, because that's a nice little question, but you'll be able to do that. This one also, you can't use less than 4 colors. And then you see that we have an invariant. So I'll stop here after doing this one last bit. Suppose K can be colored in Z mod NZ, okay? Suppose it can. Let min call sub n of K be equal to the least number of colors coloring K over all diagrams equivalent to K by Reidemeister moves. So you're like in the case of the figure 8 knot, you have 4, maybe, but I tell you it can't happen. There's one that only uses 3. But there isn't. You'll have to prove that. But in other cases, you'll have a diagram. It uses a certain number of colors, but in fact, there's some other diagram that uses less. So we can consider the min color of the diagram, and that's an invariant. This is and elusive invariant of the knot K. Not so easy to figure out what the minimal number of colors would be. I don't know a formula for it. I know how to search, but it's an infinite search. So not obvious what the min color is. We can get some inequalities about it. So that's a research problem using nothing more than what we've constructed so far, and it's quite interesting. So I'll stop there, but the program for next time is oriented Quandl and Alexander polynomial, and then we'll go on to bracket model, bracket and Jones polynomial. And we probably will start talking about virtual knots tomorrow.